Hello juniors, today we're going to see electronic assignment number 12, which is about degrees, radians, arcs, and sectors. We're beginning the last chapter that we're going to be covering this year for math. So I hope you enjoy this chapter, this last one. It has to do with trigonometry, which is what we were studying before this. So pay attention and let's see. Objectives. Number 1, find arc length of a given circle. Number 2, find area of a sector. Number 3, convert angles from degrees to radians and from radians to degrees. Okay, so it says, many phenomena that have a periodic or repeating pattern, such as tides, sunlight, and Ferris wheels, may be modeled with trigonometric functions, which is what we will be focusing on for this chapter. So here are some interesting applications of trigonometric functions to real life situations, and these are all very interesting topics maybe for you to analyze in your math internal assessment or math projects, right? For example, can I visualize the amplitude, pitch, and frequency of musical notes? Or how can I model my height on the Ferris wheel? This is very interesting. Then, what time is sunset in Bali on my birthday? A very interesting application. Maybe if you wanna predict at what time you will have a sunset on your birthday, for example, in Asunción or wherever, Samber or whatever, you can make a model of the sunset time in Asunción or Samber and make your prediction, right? And finally, what is the best time to surf? There are times in which the waves are higher or lower than other times, right? It is said that at night, for example, the tides tend to increase, right? So that's something that maybe can be modeled using these trigonometric functions. And all of these are repeating patterns, right? Waves never end. They repeat and repeat and repeat throughout time. Also sunset, right? We have sunset every day and so on. So these are all examples of trigonometric functions. Okay, so let's start with some basic stuff. Degrees and radians, for example. This is something that we have talked about already. The relationship between these two different types of measuring angles. So it says 1 full rotation is 360 degrees or 2 pi radians. That means that the relationship between degrees and radians is given by this, right? 360 degrees, 1 full rotation is 2 pi, which is also 1 full rotation in radians. So we can also take this deduction, 180 degrees will be pi radians. So how do we convert from degrees to radian? It's simple. We just make this proportion. We're going to say that 180 degrees is to pi, as, for example, if we want to convert 30 degrees to radians, as 30 degrees is to x radians. So we do the proportion, right? And it's 30 times pi divided by 180, which is exactly what we have here. So we get that 30 degrees, it's equivalent to pi over 6 radians. And if I want to convert from radians to degrees, it's exactly the same thing. But now we have both information for the angle in radians, right? So for example, if you want to convert pi over 6 radians to degrees, it's 180 is to pi as pi over 6 is to x, right? So we write the proportion and we're going to say that it's pi over 6 times 180 divided by pi. So we do that, pi over 6 times 180 divided by pi. We simplify terms, we get 180 divided by 6, and we get as a result 30 degrees. That means that pi over 6 radians is equivalent to 30 degrees. Okay, so here's the summary. To convert degrees to radians, we multiply by pi over 180. And to convert radians to degrees, we multiply by 180 over pi. So that's simple, right? You don't even need to memorize this. You just need to apply the proportion, and that's it. So let's see some basic examples just to ground the concept. It says, convert these angles to radians. So we have all of these angles in degrees. We want to convert them to radians. So for 30 degrees, we already did that in the example, actually. We can say that 30 degrees is to x radians as 180 is to pi. This will be our proportion always, right? So x is equal to, and we do this times this divided by this, the famous regla de tres in Spanish, right? So this would be pi times 30 divided by 180. With simplified terms, for example, 0 with 0 and 3 with 18, this is 6, right? So we get as a result pi over 6 radians. We can write this as rad only, and that's fine. So 30 degrees is pi over 6 radians. Then 45 degrees, we're going to do exactly the same thing, right? For 45 degrees, we're going to have that 45 is to x as 180 is to pi. So if we write the expression directly, we're going to say that, let me separate this first. If we write the expression directly, we're going to say that x is equal to pi times 45 degrees divided by 180. If we simplify terms, 45 divided by 180, I think that's 1/4. 180 divided by 45. Yes. So this is pi over 4 radians. Pi over 4 radians. This would be the answer for 45 degrees. And finally, for 60 degrees, it says we want to convert 60 degrees to radians, so same thing, right? Pi times 60 divided by 180. With simplified terms, for example, 0 with 0, 6 with 18, and we get the result, which is pi over 3. Pi over 3 radians. So these are the converted angles from degrees to radians, okay? Forgot to separate this. Kind of like there. Okay. And then we're going to do the opposite. For part B, we want to convert from radians to degrees. So that's what we're going to do. For part B, it says convert this angle to degrees. So we have 2 pi over 5, first of all. So let's write our proportion first. We're going to say that 2 pi over 5 is to x degrees. We don't know how much is that yet. As and our proportion here, we have to write pi is to 180 degrees. Remember that in one side I should always write in degrees, and on the other side I should always write in radians. I cannot mix the order there, or else the result will be incorrect. Okay, so if we do this proportion, we're going to say that x, the value we're looking for, is equal to, let me see if I can move this here, is equal to 2 pi over 5 times 180 divided by pi, right? That's the order in which we multiply. So it's 2 pi over 5 times 180, and this is being divided by pi. So I then simplify terms, for example, pi with pi, and then I can simplify 180 with 5. That would be 180 divided by 5, that's 36, and 36 times 2, so let me write 36 here. 36 times 2, that's 72. That means that all of this gets simplified to 72 degrees, and that would be the answer for this angle. Okay? Then we're going to do the same thing for pi over 9. We're going to say that pi over 9 is to x degrees as pi is to 180. 180 degrees. I could also use, if you want, you can also use this equivalence. 360 equals 2 pi. It'll be the same thing. So from this expression, we're going to say that x is equal to pi over 9 times 180, and all of this is being divided by pi. So with simplified terms, pi goes out with pi, and 180 divided by 9, that's 20. Yes, 20. So the value of x is equal to 20 degrees. So this is how we convert from radians to degrees, okay? Simple and easy. This is just as a review of some basic concept you should already know. Okay, so let's move on. Here's a summary of the different special angles that we we normally use in IB exams, especially for paper 1 where you're not allowed to use calculator. So this is a summary of the conversions if you wanna kind of if you have a good picture memory, then this would be good for you. Like for example, 30 degrees, its equivalent in radians is pi over 6, 45 is pi over 4, 60 is pi over 3, 90 is pi over 2, and so on, right? So you have the relationship between degrees and radians, and here you have the cosine and sine values for each angle, right? If you visualize here in the x-axis, the x-axis will always correspond to the cosine values, while the y-axis will always correspond to the sine values. If we zoom at this triangle over here, for example, the 30 degrees triangle, you would see that sine, for example, is this side over here, right? Because sine is opposite, let's write the angle here, it's opposite over hypotenuse. And if we assume that this is a circle with a radius of 1 unit, then the opposite is sine, the hypotenuse is 1. So if we write opposite over hypotenuse, we're going to write sine of the angle divided by 1, and we will get sine of the angle. So just for you to remember, sine corresponds to the y value of the coordinate, while cosine, which is adjacent over hypotenuse, corresponds to the x value of the coordinate, okay? That's a trick for you to remember. So, as I told you, this is the summary of the values for you to remember, okay? This will be especially helpful for paper 1 where you are not allowed to use your calculator. But if you remember the left hand rule or the hand rule to remember the special angle values, then you don't even need to remember this circle. But just in case, I'm putting it here, just in case you like this. Okay, then we have these concepts: arc, sector, chord, and segment. Let's see what this is about. It says, an arc is part of the circumference of a circle. If you take a look at this circle over here, we have this is an arc. Or if you take a look at this one, it's easier, right? This red line here on the circle, on the circumference actually, is the arc. It says, minor arc AB is the shortest distance between 2 points A and B on the circumference of a circle. Major arc AB is the longer distance around the circumference from A to B. So this is the minor arc. But if I consider this arc, this would be the major arc, okay? Okay, then it says, unless otherwise indicated in a question, we assume arc AB refers to a minor arc. So we are always going to be working with the minor arc unless the exercise tells me the opposite. Then, what is a sector? A sector is a region enclosed by 2 radii and an arc. Unless otherwise indicated in a question, we assume sector AOC refers to the minor sector. So the sector would be all of the all of the purple area, all of the purple shaded area, right? This is a sector. So arc is only the external part of this, while the sector is all of the area inside, like cutting a piece of pizza, right? That would be the sector of a circle. Then it says, a chord is a line segment joining 2 points on the circumference of a circle. So this is an example of a chord, right? It's any line that cuts the circle. Yes, any line that cuts the circle, basically. And finally, a segment is a region between a chord and an arc. So if we look at this graph, here we have this segment, right? The region between a chord and an arc. So this is the arc, this is a chord. So the region inside of it is what we call the segment, right? It's kind of related to the sector, but it's only it's smaller actually than a sector. We're going to be seeing this, how to work with this later on in some exercises. Then it says, any central angle in a circumference is a fraction of 2 pi. So you can calculate the length of an arc, the length of the arc the angle subtends as a fraction of the circumference. So here we have a formula which is available in the formula booklet. that allows us to calculate the length of an arc. The length of an arc, as I told you, is this distance over here, right? The distance on the circumference. How do we calculate that? It's easy. We just need to multiply the radius of the circle times the angle. But it is very important. Here it says r is the radius and theta is the central angle measured in radians. If you want to use this formula here, you should always plug in the angle in radians. If you plug in the angle in degrees, you would get a wrong result, okay? And the deduction of where this formula comes from is actually pretty easy. It's just using proportion. If we want to find this arc length, we can say that, for example, that arc length, which we're looking, is to the angle theta, this angle over here, as a complete, the length of a complete circle, of a complete circumference actually, is 2 pi times radius, right? That's the perimeter of the circumference. And this is the angle that subtends that arc. It would be the complete rotation, right? 2 pi. So if you see, if I do the proportion here, I'm looking for this value L. So we're going to say that L is equal to, 2 pi r times theta divided by 2 pi, right? So 2 pi r times theta divided by 2 pi. And you see that we simplify here terms, 2 pi with 2 pi. And what do we get as a result? R times theta, which is exactly the formula that we're given in the formula booklet to find the length of an arc, okay? So that's where the formula comes from. It's just doing the proportion. Okay, now if I don't want to use this formula, which, as I told you, is available in the formula booklet, and I want to work with the angle in degrees, then this is the way you work. Actually, you need to do exactly the same thing we just did to demonstrate the formula, but working with degrees. It says one complete rotation, or the length of the arc for one complete rotation, is 2 pi r, right? So that corresponds to 360 degrees. If I'm looking for the length of an arc at an angle theta, then I will do the proportion, right? The angle times 2 pi r divided by 360. And that's what you have here. So x, the length of an arc, is theta times 2 pi r divided by 360. This is if you want to work with degrees. But normally you would work with this, but always remember the angle should be in radians if you're using this formula over here. Okay? Then it says, similarly, the formula for the area of a circle is pi r squared. The area of a sector with a central angle theta will be a fraction of the area of the circle. So if we do the same thing we did to demonstrate this formula, we would get this formula over here, which is the formula for the area of a sector. The sector is this slice of a pizza that we see in this circle over here, right? So if we do, let me show you the proportion. If we want to find the area of a sector, the area of a sector is subtended by an angle theta, right? Theta. One full rotation has as angle 2 pi radians, right? And the area of a complete circle is always pi r squared. So if I do the proportion here, we're going to have that the area of a sector is equal to this times this divided by this, right? So the area of a sector, right here, area of a sector is pi r squared times theta divided by 2 pi. And if I simplify terms, for example, pi with pi, we're going to get as a result r squared times theta divided by 2. And that's exactly this formula over here. R squared times theta divided by 2, or 1/2 r squared theta, which is the same thing. So that's where the formula comes from, basically. Okay. So same acceleration as for arc length. If you're going to use this formula, it says r is the radius of the circle and theta is the central angle in radians. If you're going to use this formula, you must work with the angle in radians. If you don't work with radians, you'll get a wrong result. Now, if you want to work with degrees, this is the way you should work. Same thing as arc length, basically. We're going to say that one full rotation, or the area of the circle for one full rotation, is pi r squared. So pi r squared is 360 degrees, as the area of the sector which I'm looking for is to an angle theta. Okay, so if I do the proportion, we're going to have this expression. X is equal to theta times pi r squared divided by 360 degrees. And this would be the formula to calculate the area of a sector using degrees. Okay, so let's see. I want to do 2 examples. Yes, because let's do these 2 examples, and then we're going to leave the class here to avoid making this too long. Okay, so let me see. For this example, it says, find the length of the arc which subtends a central angle of 2.6 radians, as seen in the diagram, in a circle of radius 7 centimeters. Okay, so let's see how we apply this formula. You'll see that it's actually pretty easy. First thing, we want to find the length of the arc. So length of the arc would be this red part over here, right? This is the length of the arc. I'm going to call this L. So if I want to find the length of the arc, I'm going to be applying this formula, r times theta. So the length of the arc is r times theta, where theta, remember, must be in radians. So if I apply the formula, we would have that the length of the arc is r, which is 7 times the angle in radians. This is already in radians, so we use it like that, times 2.6. So then we get the length of the arc. If you multiply this, you would get as a result 18.2 centimeters. This is the length of the arc. Then for part B, it says, find the area of the sector. So we want to find the area of the sector, which would be, let me shade that region with orange. It will be this region over here, right? This is the area of the sector. So if I want to find the area of the sector, I'm going to be applying the second formula, this one over here. Area is equal to 1/2 r squared theta, where, again, theta must be in radians. So we can use this because this is already in radians. In case this angle was given in degrees, I would have to convert it to radians first and then use the formula. Or work this way, which I don't really recommend to avoid confusion. So the area would be 1/2 times the radius, which is 7 squared, times theta in radians, which is 2.6. So that's it. We solve this using the calculator, and we will get our result for the area of the sector, which would be 63.7 centimeters squared. Okay, so this is how we apply both formulas. This is a pretty simple example. And later on in the next electronic assignment, I'm going to show you, well, the continuation of this assignment, I'm going to show you a bit more complex exercises, okay? But I hope this was clear, and if not, please let me know. We're going to clear doubt in future live sessions. Thank you for your attention.